Okay, choose the right model. AI can analyze network traffic, user behavior and system logs to detect anomalies that might indicate a cyber threat. Machine learning models can establish a baseline of normal behavior and flag deviations. So which model is the best to use? Do we have a hit list? Well, the choice of machine learning model for anomaly detection in network traffic, user behavior or system logs depends on several factors, including the nature of the data, the type of the anomaly, and computational constraints. So here are some popular models used for this purpose. Let's start with the area of supervised learning. There we have random forest. Random forest is an ensemble learning method that's effective for binary or multi-class classification tasks, such as identifying known type of anomalies. It is highly accurate, it handles nonlinear relationships, and it is robust to overfitting. So that's a good thing. However, it requires labeled training data and it is computationally expensive for large data sets. My favorite always support vector machines, SVMs. So SVMs can be used for classification and regression. It is particularly useful for binary classification tasks where the data is mostly linearly separable. They are effective in high-dimensional spaces, memory efficient, but they require labeled data, and they are less effective with large data sets. And again, they are sensitive to parameter tuning, which allows certain attack vectors. In the area of supervised learning, we have isolation forests. Isolation forest is effective for anomaly detection in unlabeled data. It isolates anomalies based on the distance from other data points. It works well with high-dimensional data, robust to outliers, and it is efficient with large data sets. But it is less effective if anomalies are clustered together or if the dataset has significant noise. Another one is one-class SVM. One-class SVMs are useful for anomaly detection when there is a clear boundary separating normal and abnormal instances. They are effective in high-dimensional spaces, particularly useful when normal behavior can be defined clearly. But there are limitations. They are sensitive to parameter settings and they are computationally expensive. Density-based spatial clustering application with noise, easier dbScan. dbScan clusters data points based on density, identifying anomalies as points that do not belong to any cluster. It identifies clusters of arbitrary shape. There's no need to specify the number of clusters. It's very robust to noise. But it is sensitive to parameter settings. It is less effective with high-dimensional data. Again, it is attackable. The third group is semi-supervised learning, and there we have the famous autoencoders, everyone's darling. Autoencoders are neural networks used for anomaly detection by reconstructing input data. Anomalies have higher reconstruction errors. Okay, they are effective for complex high-dimensional data, adaptable to different types of data. But they require careful tuning of network architecture and training. They are sensitive to the choice of threshold for anomaly detection. And threshold, again, is something attacker can misuse. Deep learning, LSTM or CNN. Long, short-term memory, LSTM, and convolutional neural networks, CNN. They are useful for time series anomaly detection in network traffic or user behavior or for scientific data. Advantage, they can capture complex temporal or spatial patterns. They are effective for sequential data. But they require large labeled datasets. They are computationally intensive and prone to overfitting. So how to choose the right model? Well, it depends on the data type. Is it structured or unstructured, sequential or non-sequential? It depends on the anomaly type. Do we have point anomalies, bias context anomalies, or collective anomalies? And finally, data availability. Is it a labeled versus unlabeled versus partially labeled data? And of course, how much time, how much computational resources do you have? For example, if you have labeled data and you want to detect known anomalies, a random forest might be suitable. If you have unlabeled data, an isolation forest or one-class SVM might be better choice. For time series data, LSTM networks might be more effective. The key is to match the model's strengths to the specific characteristics of your anomaly detection problem. But a general rule is start simple, start easy. Start with the model you can train where you get results. If it is not working, go for the next one. Do not start with a fancy, sexy, deep learning model which you do not understand and where you do not have the control to verify the data and the output. Start simple, work, take a bit more time and test it, test it, test it. That's the most important thing. Thanks for watching.